Hi there, it's Wendy again. Today is our last new information on probability. I know a lot of you are expressing that probability is hard, and it is a lot of different formulas. If you try to keep it thinking about it in common sense terms, then that really does help. Today we're talking about probability of multiple events happening. Your note catcher calls it single stage versus multi-stage. And multi-stage, we're just saying that we want to know what's going to happen in a series of events, more than one thing. So we're going to start by talking about the probability of B occurring given that A has occurred. Now, this is what yesterday was on. This is what we did yesterday. And so this was the formula. P of B given A is where you take P of A and B, where both are true, out of only the second one being true. Okay, so that's a formula we used on yesterday's, all throughout the work time yesterday. And some of you came to office hours, and really, I think it did really help a lot. So I do recommend you guys coming to those. So first of all, it says just rewrite the formula solving for A and B. So over here, if we want to solve for A and B, we're literally just going to divide both sides. I'm sorry, we're going to multiply. It is being divided. We're going to multiply both sides by P of A. Well, when we do, we get the probability of A times the probability of B given A equals the probability of both A and B. And then they're asking us, what do we do if they're independent? Well, if they're independent, we know that this given A part has nothing to do with B's probability, because that's what we found yesterday, that if they're independent, then B given A is the same as just B. And so if we just copy the formula, P of A and B equals P of A times P of B given A, and then we realize that it's really just P of A times P of B. Now, this is really complicated and a lot of probabilities in here, but it's super simple. Basically, if two events are completely independent, you just multiply their probabilities together to find out what they are in a multi-stage experiment. So again, this is going to get a lot easier. Just follow along with me and you'll see. These are how we got the formula. You're not going to have to memorize how we got the formula. You just need to know how to use the final formula. All right, so let's go down to example 2. All right, and you're going to see some of the answers, but that's okay because we're going to walk through them. So consider the spinner below. And it says the spinner is spun twice and the result is recorded. Are the outcomes of the two spins dependent or independent? Well, when we spin this, what I spin the first time has literally no impact whatsoever on what I'm going to spin the second time. So they are completely independent, because I can spin it 15 times and it doesn't matter what I got the times before. It's whatever I spin that one time. So then knowing that, this is going to seem logical then. So it says, what's the probability that you'll get an even number on the first spin and a number greater than 5, so one of those three, on the second spin? So we're looking for what happens, what is the probability that if I spin it 2 times, which we know are independent events, and the first time I'm going to get an even and the second time I'm going to get a number greater than 5? Well, we just multiply the individual probabilities. So first, the probability I'm going to get an even number is 1, 2, 3, 4 out of 8. So 4 out of 8 times the probability I'm going to get greater than 5. Well, that's 3 out of 8 that are greater than 5. So that's 3/8. I'm just going to reduce my fractions here because they're easy. So this is 1/2. So 1/2 times 3/8 is just 3 over 16. So the probability that I'm going to spin even on the first spin and greater than 5 on the second spin is 3 out of 16. Okay, so hopefully that makes sense. Now this one gets a little more complicated, but it's logical if you think about it. So what is the probability you're going to spin a prime number and a perfect square, but in either order? Now this in either order means that you have two separate scenarios. I have my shadow in there, but two separate scenarios. Okay, so what we're looking at is, all right, I could have a prime number on the first spin, which there are 4 prime numbers, 2, 3, 5, and 7 out of 8. And then I could get a perfect square on the second spin. Well, there's only 2 perfect squares, 1 and 4 on the whole spinner. So that's 2 out of 8. So if I reduce my fractions, 4/8 is just 1/2, 2/8 is just 1/4, and I multiply, I get 1/8. Now, what if I want to get those in the opposite order? What if I want to know, what if I spin a perfect square first, then a prime? Well, the perfect square is still just 2 out of 8. The prime is still just 4 out of 8. And when you multiply, of course, you still get 1/8 because they're independent. So the order doesn't matter. Now, the question was, what is the probability we could get it in either order? So that means, what's the probability we could get a prime and then a perfect square, or we could get a perfect square and then a prime? So that leads us to this part. This or, when we have to have 2 completely separate things we're looking at, we could get this or this. Well, that's when we add them. So we could get prime or perfect square, or we could get perfect square and then prime, and then so you add them and reduce and get 1/4. So up here, when you're just saying, what's the probability I'm going to get one and then the other, you just multiply. But when I have a couple of scenarios where I could get this scenario or this one, I have to add them. Okay? All right, so let's go back up to the top and go to page 2. All right, so here is the rest of the note catcher. So it says, now we're talking about with or without replacement. Now, I love these because this is realistic. So we have a class of 12 girls and 8 boys. A group of 3 is picked to give a speech. If I pick students at random, what's the probability they're all going to be boys? Okay, so that means out of the total of 20 students, I have 8 boys, right? So my first probability of getting a boy, the first time I pull a name or pick a student at random, I'm gonna have a chance of getting 8. There's 8 boys out of 20 students. So 8 out of 20. So that's logical. But now I've taken one boy. I've already chosen him. So he's taken out of the mix. And I've also removed a student because that boy was one of the students. So now I only have 7 boys left out of a total of 19 students. So that's the likelihood of my second event happening where I get a boy. All right, and then what if I want to choose a third boy for his speech? Well, now I'm down to I've already picked 2 boys' names. So what's the probability I'm going to pick a third boy? Well, now I only have 6 boys, and I only have a total of 18. So now I have 6 out of 18. So does that make sense? So my first random shot at picking a boy to give a speech was 8 boys out of 20 students. Once that boy's name was picked, it wasn't an option anymore to pick him. So the second chance would have been 7 boys out of 19, and so on. So then what's the probability when I have all 3 of these? So that means I'm taking the probability of the first one and the second one and the third. And that's when we multiply, when I just have events in a row. So I multiply the first probability times the second times the third. Now this is going to end up being a big number. So you end up getting 36 out of 6,840. You can just divide that on a calculator, round to the nearest hundredth, and you get 0.05 or 5%. So out of a group of 20 students, there's only a 5% chance that I would pull 3 boys' names in a row in order to give the speech. All right, so that's called the multiplication property, obviously, because you multiply them to find out more than one event. All right, so let's look at example 4. Say that a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches would fail is 5%. So we know if one switch fails, there's a 5% chance one switch out of the 3 would fail. What's the probability all three could fail? That would be horrible. So in case of an emergency, what is the probability? We have 3 switches put in place. What's the probability that all 3 are going to fail if each one has a probability of 5%? They are independent of one another. So one doesn't have anything to do. If one fails, it would be completely random if the other one would fail. So we're going to call S the probability that it's going to fail. So we want to know what's the probability that the first switch fails and the second one and the third one. And they're completely independent of one another. All right, well, the first probability would be 5% or 0.05. The second switch has a probability of failure at 5% and the third. So we would just multiply all 3 together and that's our answer. And look how small, which is why they put 3 in place. There is a 0.0125% chance that all 3 would fail, which is why it seems like you're pretty safe in that emergency. All right. So now we're going to go to example 5. So now we're talking about combining some things. So this one gets more complex, but again, just use common sense. So a company was determining the effectiveness of its warranty sales on computers. They took data on a number of customers that purchased warranties on 2 different brands. If a customer is chosen at random, what's the probability they did not purchase a warranty? Okay, so we have to know what's the probability that they bought the first computer. They have 2 brands, right? They bought brand 1 without a warranty, or they could have bought brand 2 without a warranty. So we have 2 scenarios, okay? So here's our data. So we want to know the probability of choosing computer 1, type 1, and no warranty, or type 2 and no warranty. So first of all, we have to figure these individual ones out, and then we have to put them together. When we figure individual ones out, that goes back to up here at the top of the page that I've already scrolled off, where you have individual events and you just multiply them together. So that's what we're going to do here. The probability that we'll get type 1 is 68%, and that we'll get no warranty on it is 35%. So we're simply going to multiply those together. Now, why is it 0.65 and not 0.35? Well, this is the probability they wanted the warranty. So if you subtract that from 100, you get 65% that did not want. They did not want the warranty. So 35% wanted it, but we want to know who didn't choose a warranty, and that's 65%. So we multiply 68% times 65%, and we get this number. Now we're going to do the same thing for number 2, type 2. 32%, and then 56 want the warranty, so what percent doesn't want it? Well, if 56% wanted it, that means 44% don't want it. So 32% times 44% means that 0.1408 is our probability that they bought that type and didn't want the warranty. So now we have each warranty, and now we have that or. So we want to know if this is going to happen, what's the likelihood this is going to happen or this. So now we have both of them, the first scenario or the second one. All right. So that's when you just add. So you take the first probability that you calculated and add it to the second, and you get this, or 58.28%. So hopefully that helped. Please use this video and these notes in order to help you with your work time today. I hope you have a wonderful day. This is the last new topic. We're going to have a tiny mini quiz tomorrow that you can use your notes on. And then I'll give you an official review tomorrow as well. And you're going to have the whole weekend and Monday to work on that. And you'll have a test that's for a test grade that you'll have Tuesday and Wednesday to work on, and we'll finish prior to the break. Have a wonderful day. Remember, I'm doing office hours every single day now from 1 till 1:30 if you ever have any questions. See you soon. Bye.